In this module, we will be covering the basics of diving physics, including a review of the units of measure and an overview of pressure as it relates to diving. We'll review relevant gas laws and how they apply to diving operations. As it relates to diving physics, either the US standard system or the international system can be used based on personal preference. In the subsequent modules, we will typically use the US standard system when working through formulas and dive planning scenarios. One important point that must be emphasized is that when working with formulas that involve temperature as one of the variables, temperature must be converted to absolute in order to obtain the correct result. Since we're using the US standard system, absolute temperature will be calculated in Rankine, which is temperature in Fahrenheit plus 460. Pressure is the weight or force acting upon a unit of area, usually measured in bar, psi, or atmospheres. Atmospheric or barometric pressure is the pressure exerted by the Earth's atmosphere. To quantify this, a 1 square inch column of air extending from sea level to the top of the atmosphere weighs 14.7 pounds. Therefore, at sea level, atmospheric pressure is 14.7 psi or 1 atmosphere. Hydrostatic pressure is the weight of a column of water acting on an immersed body at a specific depth and impacts the body equally in all directions. To quantify this, a 1 square inch column of seawater 33 feet deep weighs 14.7 pounds, or 1 atmosphere. We know this because 1 cubic foot of water equals 144 square inches, and 1 cubic foot of salt water weighs 64 pounds. To get psi, we divide weight by area. Hydrostatic pressure increases with depth at a rate of 0.445 psi for every foot of seawater, or 0.32 psi for freshwater. Absolute pressure is the sum of atmospheric and hydrostatic pressure. This is especially important when presented with a scenario that requires an answer in PSI-A or PSI absolute. Remember to add 14.7. Gauge pressure is simply the pressure being measured without taking into account atmospheric pressure. For example, if you attach a gauge to a scuba cylinder and it reads 0, it still has 14.7 psi in it. But since we are not taking atmospheric pressure into account, the gauge will read 0. Gas laws are subject to three interrelated factors: pressure, volume, and temperature. Keep in mind that a change in one results in a measurable change in one or both of the others. Boyle's law, as shown here, applies to diving when addressing aspects of barotrauma or squeezes in the ear and other air spaces. You've likely experienced this when diving, snorkeling, or traveling on an airplane. As pressure changes, the membranes of your ears either bulge inward or outward. Unless you equalize that pressure, membranes can rupture. This is commonly done using the Valsalva maneuver, where you push air out with your mouth and nose closed until the pressure is equalized and the discomfort is relieved. Here are a few more examples of how Boyle's law applies to diving. As you look at this table, you will see that the greatest volume changes happen in the first 10 meters or 33 feet of depth. This is typically where divers will embolize. For instance, if you took a deep breath of air at the surface and held your breath, that volume of air would be reduced by half when you reach 33 feet of depth. After that, it's a little bit different. Diving down the next 33 feet, the volume is reduced by 34%. As you continue to dive, the volume change lessens even more. In case you don't remember what an embolism is, it refers to gas bubbles in the circulatory system caused by gas or air passing into the pulmonary veins after rupture of the alveolar vasculature. If you look in Canvas within Module 3, we have a video listed called The Science of Water Pressure. This can help you further understand Boyle's Law in case you would like a deeper dive. Work through the challenge question to gain a better understanding of Boyle's Law. It is important to note that in this question, the diving bell is a rigid container that is not collapsible or expandable. The air is compressing or expanding depending on the water pressure, but the container itself is not collapsing or expanding. Remember when you're trying to work through these challenge questions that you need to follow the order of operations. Charles and Lusak's laws address volume and pressure changes with respect to absolute temperature. Keep in mind the general gas law states that when you have a change in one variable, you will have a corresponding change in one or both of the other variables. Dalton's law is the law of partial pressure. In a mixture of gases, each gas exerts a pressure that is the sum of the total pressure being exerted. For divers, partial pressure is important in respect to how it affects the body physiologically. The human body has a wide range of reactions to various gases or mixtures under different conditions of pressures. Henry's law addresses gas absorption. This relates and ties into decompression sickness. As the pressure of any gas increases, more of that gas will dissolve into any solution in which it contacts. As shown here, the amount of gas dissolved in a diver's blood will increase with depth. Whenever gas is in contact with a liquid, a portion of the gas will dissolve in the liquid until equilibrium is reached. Since depth and time underwater causes nitrogen to enter the blood, divers must allow enough time for this nitrogen to leave the blood and return to the lungs to be exhaled as they ascend. If a diver's rate of ascent is controlled properly, the dissolved gas will be carried to the lungs by the tissue's blood supply and will be exhaled before it accumulates and forms bubbles in the tissues. If the diver ascends too rapidly, the pressure is reduced at a rate higher than the body can accommodate, and gas bubbles may form, producing decompression sickness or the bends. Asking a scientist to get all of their work done in 25 minutes or one dive is not always realistic. What if they need days or weeks to perform an experiment underwater? What happens then? Going back to Henry's law, we find that this is possible. Any discussion of diving physics requires a basic understanding of tissue saturation. J.S. Haldane, who was commissioned by the British Navy, studied tissue saturation in order to develop decompression tables. He found that the body tissues saturate at different rates. Fast tissues like the brain and spine saturate quickly in half-time increments. For instance, if a tissue is classified as a 10-minute tissue, this means that at 10 minutes, the tissue will be 50% saturated. Then, every 10 minutes after that, the tissue will further saturate by 50% until, in theory, the tissue is fully saturated. This was a general overview of diving physics. When presented with questions related to diving physics, this quick review should be valuable. Additionally, this reference table is a quick guide to pressure conversions. The T formula can help you solve for unknowns in many diving physics applications. Keep in mind that partial pressure and total pressure are in absolute. Atmosphere's absolute is depth plus 33 divided by 33. For example, say we want to know the partial pressure of oxygen in a typical air tank at a depth of 66 feet. Our total pressure is 66 plus 33 divided by 33, or 3 ATA. Air in our tank consists of 21% oxygen, or 0.21 converted to a decimal. 3 times 0.21 is 0.63. Since our threshold for nervous system oxygen toxicity is 1.4, we know we can dive this mixture to a depth of 66 feet. Here is a quick reference table for absolute atmospheres. Hopefully, now you have a better understanding of diving physics and the application of the gas laws. Now, here you have some videos that we've put together for you to help you as you learn more about physics, the effects of pressure, and the science of water pressure. This is meant to complement the slides. Thank you very much for listening, and I hope you enjoyed.